Okay, we start a completely new topic. The topic is going to include vibrations of structures, because one of the things that's very important in acoustics is the interaction of sound pressure with structures. And when it does that, of course, structures vibrate. So we'll have some idea of how structures vibrate, and we'll use plates as an example. But before we get to it, I want to talk a little bit about Fourier transformations today. Okay? And I'll explain why we want to do that and why that's important. Fourier transforms. In the other class, we talked about Laplace transforms, Fourier series, but this is a little bit different. The reason we use transformations, does anybody know why? Why do we use transforms?
The continuous derivation.
That's for series. Okay, and one of the values that transforms provide us is when you have an integral equation or a differential equation, it will reduce it into a linear equation, or polynomial, I should say. Okay, you can get rid of integrals and differentiations and make it a polynomial equation, for which solutions are easier to come. And the second one is it gives you a content, spectral information. So in our case, the two things we want to do is transform time signals, like sound pressure, etc., into frequency domain. Okay? Remember, we have been using e to the I omega t. You'll see that that's actually a Fourier kernel of transformation that relates frequency and time. And that's a representation for a single harmonic motion. Similarly, though, another important aspect of it is we transform space, spatial variable, into waveform. Okay, we'll call it kx, into the wave number. Sorry, okay, and wave number. The wave number, as you know, is related to the wavelength. So these are the relationships. So when you have a time frequency transform, let's okay. Now, this is a definition of Fourier transform from time to frequency. Okay? Let me have your eyes over here. It's an integration from time minus infinity to plus infinity. For all times, you integrate a given signal. Okay, multiplying it by e to the I omega t. That's called the Fourier kernel. And then the result will be still, of course, an x, but no more time dependence, only a frequency dependence. Now, there are some rules involved in this, okay? The eta here must satisfy certain conditions, convergence, etc., for the integral to be, for you to be able to take the integral. I'm skipping the details. It's somewhat beyond our what we are going to do in this class. But in general, this gives you the description. Now, if you know the Fourier transform of a variable, then you can obtain the function itself by inverse Fourier transform. Once again, minus infinity to plus infinity. This time, it's slight difference, okay? This time, we take the transformed value and integrate it, but need to pay attention to this, minus I omega t as opposed to plus. Oops. And we integrate it for all frequencies. Now, when you go and look at reference books, math books, etc., it's very possible you'll see the definition such that this will be 1 and this will be 1 over 2. In fact, there's a pi here, sorry. Please include this. Yeah. In many cases, okay, you'll see the first one as 1, second one as 1 over 2 pi without the square root. But this is a much simpler and straightforward way of following and avoid confusion. This is a definition. Okay? Now, and these two are called a Fourier pair. A Fourier pair. Similarly, we can say space wave number Fourier transform. In this case, of course, we have kxt. And similarly, oops. Okay. Of course, the complete transform from space-time to wave number frequency domain is very similar. It's a double integral in this case. Okay. Okay. In shorthand, sometimes we express, for example, Fourier transform of a time-dependent function to be in the frequency domain, and inverse Fourier transform also is another shorthand description. Okay. All right. In general, a transform is complex. So we would think about it in terms of a magnitude and a phase information. Okay? And when the function itself, okay, when the function itself is real, then the transform has the property that when you change the sign of the frequency, it's equal to its own conjugate. Okay? Now, there are some interesting relationships that will be helpful to you, and you need to remember them. Let me write the transform equation one more time just for the time portion. Okay. See, for omega 0 in this relationship, yes.
Why did you say when it's real?
I'm sorry, say again?
Is it possible that it's not real?
Yes. Yeah. Sometimes you have a complex expression, even in time. It's an expression. Yeah. Phase information can be expressed in complex terms.
It's in time domain.
I know. But these are functions. Yeah, not actual real measurements, but functions, yeah. So for real functions, that's a given property, yeah. Okay, similarly, okay, take a look at these last two equations and see what they say to us. The integral of a function from minus infinity to plus infinity is equal to its value, DC value, at zero frequency. Okay? So if you know the spectrum, if you happen to know the spectrum of a function, you can get its entire integration by looking at the DC value. And similarly, the value of a function at t equals 0 gives you the integral of all the frequencies. Okay? Now, something even more interesting than this is called Parseval's theorem. Okay, and Parseval's theorem gives us very useful relationship. Let me just see. I wonder. Let me hold off on this because I don't know if I like this. I think it's missing something. I want to check something in this Parseval's equation, okay? Let me see in my handouts if I have the right. Okay, Parseval's theorem, which I will cover next time. But convolution expression. How many of you have seen convolution? Are you familiar with convolution? 1, 2? Have you heard of it?
Yes, I
You don't remember? Okay. Convolution is basically, let me write the equation first and then I'll describe what it is. Where does one use convolution? Anybody remember? Do you remember?
I think in control in order to obtain frequency response.
But yeah, right now there's no frequency here, but that's right. I mean, control is one. Another one is, the other day in the other class, we spoke about responses, transfer function, etc. What we didn't talk about is, in time domain, you have something called impulse response. Impulse response is when you give an impulse to a system, the result is basically what's called an impulse response. When you have an impulse response, then you can actually obtain the response due to any input. Okay, that's where convolution comes in. Okay, it convolves these two. Now, when you take a Fourier transform of this, convolution obviously is an integral with respect to t with a time delay tau. Okay, but when you take a Fourier transform of this, you'll see it gives you some very interesting results. So let's see if we can do a Fourier transform of convolution. Okay. This is our convolution in tau and our transfer kernel, and we take the integral with respect to tau. Okay? You see, this, we haven't done anything that's unusual. This is our variable c tau. We're trying to take a transform of this. What we do is express t minus tau with a variable u. So, okay, make it. So du d tau. If we go here and make all the proper substitutions, yeah, this is what I didn't want to do. I want to change something. Can I have everybody's attention just for a moment? It just screws up the signs. Let's go back up here to the convolution. I'm going to change these two, okay? It makes no difference in this equation, but it makes it difficult down here if I keep it that way. So just change these to tau minus t, please, okay? And next we come down here, okay? Tau minus t, and of course, tau minus t, and this is plus. Now, for tau, now we're happy. I omega t e to the I omega u, and we have du and dt. Now there's something oh, I'm missing one integral here, please. So you can see y1 t e I omega t dt. You can see now that these are both Fourier transforms of each of the functions. At least, okay. Okay. Another way to express convolution is you take these two and put an asterisk between them. That's a sign of convolution, okay? y1t asterisk y2t. That represents this integral, convolution integral equation. Okay? So this, except for this extra, we can see that convolution and frequency spectra of two, multiplication of the frequency spectra of two functions are the same. Now, what does this mean? Go ahead.
We can take the Fourier transform of the function, make the operation easier.
Exactly. Yeah, very, very simple. Much simpler. Okay. Now you're replacing a convolution where you would find the output based on the input, etc., by taking Fourier transforms of two functions and multiplying them. As simple as that. And these are very routine calculations in all signal processing, dynamics, electronics, controls, and so on. So the bottom line is, one more time, the convolution and its Fourier transform are a very important pair from our perspective. One other thing that I'd like to mention is Fourier transform of derivatives. Fourier transform of derivatives. I'll describe why that's important. If, for example, a function's Fourier transform is something called phi kx, or yes, doesn't matter, but they both start with f. Okay, the derivative the nth derivative of that function's Fourier transform you can see how life can be much, much easier. Now suddenly you have gotten rid of the derivative, okay, nth order derivative, and multiplied with just an nth order coefficient. Okay? Why are we paying attention to this? Because plates, structures have derivatives involved in them, and when we solve it, we're going to apply Fourier transform and solve the problems a lot easier. In fact, we have already done that. Okay? If you recognize the pressure equation, for example, what we did was we did take basically a Fourier transform when we wrote these in terms of wave number. Okay, now we're going to do it more formally because it's a more complex spatial relationship. The last of these is autocorrelation. How a function, and autocorrelation is another way to describe a function in signal processing. Let me write that down for a second. Autocorrelation, let's call it AX, is an integral of a function from, let's see, okay, with a delay from infinity. Fourier transform of an autocorrelation. Can you take 2 minutes and see if you can do a quick Fourier transform of it? based on what you have learned. A quick Fourier transform of autocorrelation. Much like what we have done here, slightly different. Okay, I will give you the result, and I'd like you to work on it when you get back. If autocorrelation is okay, see if you can get that. Now, there's another concept called cross-correlation. After you write this, let me just have a minute of your time. Okay, there's another function called cross-correlation. And what that means is having two different functions. And what that does for us is it's a comparison of functions, the relationship between the functions. And its Fourier transform is called cross-spectrum. What it does for you is it compares two functions, okay? And let me just describe why it is important, and then we'll move along. In fact, I'll do this. Oops. And let's make these in time, so you'll like it. You'll appreciate it a little bit better. Okay. Oh. A spectrum is, for speaking for time domain signals, is its frequency content, okay? Let me make it very simple. If you have a sine wave, a pure sine wave from infinity to plus infinity, what would be its spectrum? A single frequency, right? So what'd you say? Oh yeah, sorry. Oh, can I repeat? Yes. If you have a pure sine wave from minus infinity to plus infinity, you have a single frequency representation. So if you take its Fourier transform, basically you get a delta function at a particular frequency. Now, if you have a different sine wave, again minus to plus, then you have a different one. Okay? If you multiply these two, you take complex conjugate of 1, what would be the result? 0. You're looking at me puzzled. How come? You multiply this with that. See this frequency with this frequency with that. Okay. That means their cross spectrum is 0. That means their cross correlation is 0. And physically what that means is there's really no relationship between these two. Why do we care? Well, if you have a system, okay, and then if there's some excitation coming into it and some response comes out of it. But you also have other types of excitations, other things coming out. So when you make this measurement, you want to know how much of it is due to this, how much of it is due to this, due to that, and so on. So you can take one of the things, this is a simplistic way, but you take a cross spectrum of these signals. You measure them, take Fourier transforms, multiply them. Now you can say, what if they contain the same frequencies? Well, then you have a little bit of a problem. Then you need to look into further information, phase information, etc. In acoustics, this is important. For example, in underwater acoustics, you don't see anything. You're detecting different types of sounds, like sonar. Okay? You send out a signal. Signal is reflected back, but you want to know where it's coming from. What kind of signal? And these are some of the signal processing techniques that are used. So that's what cross spectrum does for you. It compares two signals. If you also take into account the phase information, it will tell you if there's some relationship between them. That's why these are important. Okay? All right. Now, we have 10 minutes. I want to describe just a little bit what we're going to do from next class on. And we're going to talk about plates. Do you have any questions about Fourier transforms? Class was more excited when you were up there looking, studying. Now you're kind of relaxed, almost sleeping. Okay, I think I know what to do. Bring you up here every time. All right. Any questions on Fourier transforms? No? Okay. I'm sure you will have some. Plates. And why do we study plates or structures like plates, shells, membranes, beams, and so on? Because they become important when we consider them in the context of acoustics and their response to sound. For example, even in a nuclear power plant, just nuclear power plant, the heat exchangers, which are very, very critical to cooling the system, the acoustic resonance due to pressure in the fluid can actually resonate them so much that they break off. So it isn't just for hi-fi or underwater acoustics, but all sorts of different types of applications where sound and structural interaction is important. Not to mention airplanes, rockets, missiles, and so on. So when we look at plates, next time, we say, okay, we'll start with what's called an infinite plate. The reason we will start with infinite plate is because what happens at the edges acoustically is a complicated issue, okay? It's a complex problem. Before we get to it, we'll look at infinite plate, meaning we ignore what happens at the edges. And from our perspective, a plate vibrates. When it vibrates, we'd like to look at it at different frequencies or at different wavelengths. So plate, an exaggerated shape, like a string, when you shake it, it vibrates in its own bending waves, okay? So we'll learn about these bending waves a little bit next time. So now, if I somehow vibrate the plate at the bending waves, what I'm really doing now is I just tap on this, is I'm exciting a number of bending waves, because it's an impulse excitation, which theoretically contains all frequencies, okay? But if you take one of these bending waves, as it just travels, it moves the fluid. in this case air. It moves it, and that radiates into air as sound. Okay, we're going to look into that problem. Now, if you just look at this by itself, we would have a plate impedance and its displacement, and it has to be excited by a function of time. But there's one other thing that's involved in this. Where is it excited at? Okay, so plate is a two-dimensional object. So you would look at the position of the forcing function on the plate also. And this is a very important parameter for us. And I will describe the impedance next time. Impedance will have its stiffness, inertia of the plate. They will become important. And later, instead of this force, we will look at the sound pressure that's acting on it. Now, what you will find interesting, especially if anybody is interested in underwater stuff, underwater acoustics, is as a plate is vibrated somehow, let's say mechanically, it starts radiating sound. But now this acoustic field has a pressure, and the boundary condition tells us that it's acting on it. Okay? You see what I'm getting at? If this is a plate, and I'm inside here, and there's water here, okay? I apply pressure on the inside, sound will start radiating. Well, that radiated sound has, if you look at the boundary condition, has a pressure field now, okay? That pressure is acting on it. So you have, let's say, a force that's pushing out, and you have a pressure acting on it, but on its boundary, if this is y. Do you see the big picture of what goes on here? So this is what's called a fluid-loaded plate, or radiation loading. You radiate sound, but it loads back onto the plate. And there are some critical results that come out of this. So hopefully in the next 1 or 2 classes, we will cover all of this and make some sense. Any questions?
May I ask
Yeah.
general question?
Sure.
When I was looking for books, there are lots of books about underwater acoustics. Why?
You mean at the library or in general? Oh, is that right? Well, okay. Why underwater acoustics? Because underwater acoustics is fundamental to, number one, submarines. It's a very, very big deal. And number two, for exploration of the ocean bottom. It could be for petroleum or just to measure the topography of the bottom of the ocean. So those are the two main reasons why. But there has been a lot of research and investment in underwater acoustics. There are two things, there are two goals. One is you want to be as quiet as possible. Secondly, you want to be able to measure everybody else who's trying to be quiet. Okay? In fact, the technology is so advanced now that very sensitive measurements can be made from miles and miles away. Okay?
I was also looking for the lecture notes of MIT. Most of the acoustic topics about underwater acoustics.
Yeah, that's mainly because they have an ocean engineering. They did have an ocean engineering department. It closed down now. But until then, there was a lot of work in that area. Okay, well, thank you.